Modern infrastructure relies on a hidden network of volatile arteries, connecting massive industrial power grids directly to the glowing server banks of global data centers. These conduits must simultaneously withstand high electrical stress, heavy mechanical crushing loads, and the threat of catastrophic structural fires. Designing these systems requires navigating a contradictory web of regulations, where a single asset must satisfy the International Electrotechnical Commission while adhering to specific regional mandates, like the Bureau of Indian Standards. To manage this complexity, engineers use a standardized alphanumeric nomenclature. A designation like A2XYF serves as a precise structural blueprint for the cable's capabilities. Deconstructing this specific high-tension asset reveals the material science and international regulatory matrix governing the global grid. Mastering this shorthand is the only way to ensure global interoperability and prevent the material mismatches that lead to multi-million-dollar system failures. The letter A identifies the metallurgical core as aluminum, which dictates the primary flow of electrons. Copper offers peak conductivity, but hot-rolled aluminum is the cost-effective standard for macro grids. Being less conductive, it requires a larger cross-sectional area to match a copper equivalent. To maintain flexibility in heavy cables, these conductors are stranded into concentric or rope topologies, allowing them to be routed through complex infrastructure. When these cores are engineered for an 11 kilovolt load, they collide with a major regulatory friction point. At the 11 kilovolt threshold, Indian standards classify the asset as high voltage, while IEC and ANSI label it medium voltage. Legacy Indian rules force loads between 650 volts and 33 kilovolts into high tension. Conversely, international standards treat this exact load as standard medium voltage. This forces manufacturers into a dual-layered engineering strategy, meeting global physical performance benchmarks while adhering to contradictory domestic labeling and certification laws. The 2X designates the primary dielectric insulation, cross-linked polyethylene, or XLPE. Legacy thermoplastics like PVC are limited by a continuous operating temperature of 70 degrees Celsius, which restricts their use in modern high-load infrastructure. Through vulcanization, polymer chains in XLPE link into a rigid three-dimensional lattice. This allows the insulation to withstand extreme short-circuit temperature spikes without melting. The thickness of this dielectric layer is determined by system grounding. Ungrounded systems require thicker insulation to handle prolonged phase-to-phase voltage stress during faults. In cables operating above 2,000 volts, the primary engineering concern is the management of internal electric field stress. Microscopic variations in the electric field can ionize the surrounding air, creating corona discharges that degrade the polymer insulation from the inside out. To prevent this, extruded semiconducting screens are applied over the core. These screens ensure a uniform electric field gradient, preventing localized discharges and extending the life of the asset. Managing thermal limits and controlling invisible electric field stress is what ultimately guarantees the cable's operational lifespan in a volatile grid. The letter F identifies the flat steel strip armor, the layer responsible for physical defense in severe environments. Flat metallic tapes provide the high crush resistance needed for direct bury applications, where the cable must survive heavy terrestrial pressure. This differs from steel wire armor, which utilizes galvanized round wires to achieve entirely different mechanical properties. Wire armor is specified for vertical suspended runs or areas prone to ground movement, where high tensile strength prevents the cable from being pulled apart. Before these armors are applied, an extruded bedding layer binds the multi-core assembly together, creating a stable circular foundation for the metallic wrap. Armor topology forces the electrotechnical design to withstand civil engineering loads without compromising the internal electrical flow. The final Y indicates the outer jacket. Traditionally made of PVC, this layer shields the internal components from moisture and UV radiation. However, standard PVC is a highly efficient fuel during a structural fire, rapidly propagating flames vertically. Combustion releases dense, vision-obscuring smoke and toxic halogen acid gas, which are primary hazards during emergency evacuations. Dense urbanization has driven a shift toward low-smoke, zero-halogen compounds, which completely eliminate chlorine and fluorine from the outer jacket's chemical composition. The Fire Survival Standard shifts the engineering objective toward ensuring active operational endurance during an ongoing structural fire. This standard relies on a hidden mechanism, refractory mica tape wrapped directly around the raw copper conductor. This unyielding layer must maintain circuit integrity for 3 hours at 950 degrees Celsius, ensuring critical fire pumps and lighting remain operational while the building burns. Modern outer sheathing functions as a heavily regulated life safety technology built to satisfy the uncompromising requirements of global fire codes. This matrix shows the interlocking complexity of international regulations, where national frameworks are increasingly forced into alignment with apex global safety standards. This harmonization reflects a permanent global transition towards thermosetting polymers and more rigorous safety benchmarks in high-density infrastructure. A new frontier is now eroding the traditional boundaries between power and data, the integration of bulk DC power delivery within high-frequency digital networks. This generates intense, sustained heat inside tightly packed LAN cable bundles, introducing a new set of thermal engineering constraints to the design of digital networks. Building the nervous system of the modern world requires a bilingual engineering approach, merging strict regional statutory compliance with the absolute physical tolerances of global electrotechnical standards.